So, hello everyone. Turns out we are not super sure as to how fast our universe is expanding today. So what I'm talking about is the Hubble tension. It is a phi sigma discrepancy between measurements of the Hubble constant from early time lambda CDM based measurements versus direct late time measurements. Now, till date, there has not been any satisfactory alternative cosmological model that has been able to explain this problem. Neither has there been discovery of significant systematical biases in experiments that can explain this tension. The usual way to address this problem is either to pull one value towards the other somehow or the other. But it raises a question, what would happen if you measure the Hubble constant from an intermediate redshift probe? And in that context, I want to talk about gravitational waves for two reasons. One, you can observe gravitational waves from large distances, and two, they are standard sirens, in the sense that if you have the waveform, you'll be able to infer the distance from which the event came, and if you can somehow measure the redshift, you have the Hubble constant. Unfortunately, we still don't have the technology to detect such events. We will in the future. But for now, what we can do is we can generate mock data sets. And we did so for certain different models of source population distribution and by assuming certain different cosmological models as fiducials. And we do this in the context of LISA and for supermassive black hole binaries. So these are the 6 cosmological models that we considered in this study, just representative. And we constrained each of them with a consistent set of data comprising of the CMB, the BAO, and supernovae, just to bring them to an equal footing. And then we use these constraints as priors to generate our mock data sets. And then we do the main thing. We do a forecasting with these mock data sets in 3 approaches. First, we do the usual Fisher matrix forecasting, which gives you an estimate on the error on the Hubble constant. In the second approach, we just pretend that the mock data sets are real data, and we do the conventional MCMC parameter estimation, and we get an estimate on the mean and the error on H0. However, this method involves assuming a cosmological model. So in the third approach, we try to reconstruct the Hubble parameter itself in a non-parametric manner without assuming any model using the machine learning tool called Gaussian processes. And once you have that reconstruction, the y-intercept of that gives you the Hubble constant. So doing these, in the first row, I quote the tension values with current data sets. For Fisher, you will see that the tensions have increased. Why? Because Fisher predicts that LISA would be more constraining on the Hubble constant than all current data sets. For MCMC, you will notice that the tension values are largely consistent with current data sets, and this acts as a consistency check in the sense that we are not doing anything funny while generating the mock data sets. But the most interesting thing happens for Gaussian processes. So the tensions seem to have reduced. This is for 2 reasons. One, the error bars have widened a little bit. But the other thing is there is a generic shift in the mean values of H0 for all the cases towards a higher value, towards a late time value. This is very surprising because in the whole analysis, we have not put any late time bias in the work. And honestly, we still don't know why this is happening, and this is an open question for future investigation. Anyway, the essence of this exercise was to urge the community to, whenever you do a forecast, you do it using different methods so as to comparatively weigh and outweigh the pros and cons of each. Right, but at the end of that, we were curious as to how robust are these reconstructions with GPs? Like how much do they depend on the instrument that we consider? How much do they depend on the fiducial priors that we consider? So to investigate that, we carried out a study using 2 different GW missions with completely different systematic biases, systematic effects, the Einstein telescope and the LISA. And at the same time, we considered fiducial priors from 2 different sets of observational data, early time and late time. And this is what we get. It's a busy slide, but I want you to focus on the left panels first. You'll notice that for ET, the Hubble parameter is constrained quite well because of its high data density, but only till redshifts of about 1.5 or so, not beyond that. On the other hand, LISA will be able to probe much deeper, but it will not have that many events detectable. So in a way, the two missions have pros and cons in terms of redshift range and data density. On the right-hand side is shown how the constraints on H0 scale with the number of events detected, and the fiducial dependence that goes into the mock generation, that is evident from these figures. And you will notice that for some of the cases, the numbers kind of coincide, Does this mean that this solves the tension? No, because this is a, forecast study based on mock generation, mock data sets, but it is exciting because when the real data comes in, maybe this will give us some real insights. So just to wrap up the second part is, I just want to say that GP is a robust tool. It is sensitive to the fiducial inputs that we give it. Also, LISA and ET both prove to be precision instruments. They will constrain the Hubble constant more than all currently available data sets. And of course, the more data you have, the better the reconstruction and the better the constraints. So I'll end with this slide where I just want to say that the Hubble tension is a notorious problem, and we think that intermediate probes are the way to go. And I personally feel that machine learning will provide valuable insights in this direction, but much work is still left to be done. And as my closing remark, I just want to say that tensions in any field are bad. Especially in this field, it means that we as cosmologists are probably not doing our jobs very well. But at the same time, this is a prospect for novelty and discovery, and that is probably what makes this very, very exciting. Thank you.
For your Gaussian processes, what kernel are you using?
So it's the Matern 7x2.
Do you think that maybe the way you're handling your hyperparameters would be influencing like your bias? Is that where it comes from maybe?
So we did try with multiple kernels, but we saw this feature across all of them. So yeah, that's it.
Sorry, I have an even more basic question than this. I don't understand what you're doing with the Gaussian process if you're already assuming a lambda CDM model.
Okay, so since this is a forecast study, when we are doing the mock data generation, we have to assume a model because we don't know what the real model is. But the way we generate the data set, we do some random sampling within that, trying to minimize that model, cosmology dependence. So in the second part, there's no model dependence. That is non-parametric, but I agree with you. There is some dependence in the first part, but we try to do some random shuffling. If you have a look at the paper, you'll be able to understand better to minimize that. But otherwise, we don't have anything else to do.
We can discuss.
Sure, please.
Hi, thank you for the talk. Are you using bright sirens, right?
Yes.
So I think the source of biasing on H0 could be the DL inclination angle, luminosity distance inclination angle degeneracy. There's a bunch of literature recently that investigate this, Mancarella, Xingyu, and so Xingyu Shen. So maybe you can try that.
Thank you. I'll have a look at that. Sure. Thank you.
Okay, let's thank the speaker.